I'm actually a PhD in general engineering, master's in physics. I used to teach at community college, Erie Community, and taught physics and electrical engineering and various other computer technologies. And recently, I'm happy to have been 20 years off and on at the U.S. Patent Office and retired from that place. So now we're pursuing full-time with Integrity Research Institute. And it's helped in the publication business. In fact, one of the biggest adventures we have right now is the publication of Nova Science Future Energy, the challenges, perspectives, and solutions. So if anyone would like to contribute to that publication by the end of 2019, please send in your proposed chapter. But today, I'll be talking about energy breakthroughs that are expected to have a public impact. And this talk I actually have given in the past at the World Energy Engineering Congress and also at a Breakthru energy movement a few years before that. But I keep updating it because, of course, this is an important topic. And why is it important? Well, here's a little bit of motivation for you. Recently, I've just finished a 22-page climatology article that's going into a journal of environment and climate change. And what's, I think, provocative, and I waited 13 years before I published this, is the Hansen graph that you're looking at right here. Now, this was published in the MIT's Technology Review back in 2006. Virtually no one paid attention to it. I found it to be very provocative because the carbon dioxide, sea level, and average temperature, Earth temperature, over 400,000 years are graphed here from the Vostok ice core data. And this is actually analyzed by many other scientists, but what Jim Hansen did, and also NOAA, confirms the same type of, these are ice ages you're looking at. Every single dip in the trend through 4 ice ages are present and visible on this historic graph. Of course, now the anomaly here is this 377, which was back in 2006. That was the parts per million of carbon dioxide. Today it's up to 410. Now, what the history tells you, if you're into the Gaia movement or any type of harmonics type of nature is best to follow whatever nature normally has, the natural cycle perhaps is wise. Well, we've never exceeded 290 parts per million in 500,000 years. Actually, you can go back even further. But the important part is, as you look closely at this graph, and I've done this for some of the climate deniers I keep coming across, there's always the skeptical perception that, oh, carbon dioxide has never preceded a temperature increase, which is basically what we're faced with now, a big spike in carbon dioxide and temperature going up slowly. So we wonder if this is actually historically valid. Well, the idea of CO2 being a predecessor is visible in almost any one of these segments of the graph I just showed you. It's basically just looking at the previous black line, and then as you go further in time goes to the right, the red line that follows. So I split this up into 3 segments. You can look for the black and red lines in that order. Black first on the left, red on the right, and it occurs all the time historically, and vice versa, which to me is very encouraging because that means not only do we have a carbon dioxide leader, but perhaps we can use that to also drop carbon dioxide, or vice versa, in other words, pull the carbon dioxide from the atmosphere and therefore lead the temperature back down. Now, what Jim Hansen did, which nobody else has done since then or before, was to provide a key for the graph. And as you examine this key, I certainly, personally, became more and more impressed with the impossibility. I thought it was impossible, because nature always has nonlinearities. You know, you just never find linear stuff. Well, guess what? From 170 all the way up to 300 parts per million, this is a linear relationship to temperature, to the average Earth temperature. Unbelievable. How simple could you get? And it turns out the simplicity is in this little box that I added. These are the only 2 things that I've added in the white boxes. Remind you, this is back in 2006, and then this 1 degree per 20 parts per million above the 290. 290 afterwards, please. Above 290. So if we're at 410, you can do the subtraction, which I just did on Capitol Hill at the Rayburn Building for the Energy and Environment Studies Institute, where basically you subtract 410 and 290, you get 120, divide by 20, and how many degrees do you get?
6.
Everybody agrees, 6 degrees C. What does that tell us? What is 6 degrees C? That's impossible. For years I thought that's impossible. Well, it is possible, and unfortunately we're faced with, my composite is here saying the same thing, but slowly, which is why I wrote 20 pages of an article to try to track not only the causality of carbon dioxide stoking the system, but then the experts' prediction of 1 degree every 20 years up to 2100. If we just stop at 410, no more carbon dioxide emissions worldwide, we'll still get up that 6 degree ladder to 2100 and hopefully start to level out. But there are theories of how we can level out. Okay, so that's the motivation to try to do something about energy. And of course, the clean energy breakthroughs are happening all around us, and we need to upgrade and ramp these breakthroughs so they really have an impact. And I'll show you some videos too that are very provocative, very interesting, breakthrough technologies, even a Shell Corporation one I think I snuck in here too, which they admit is going to be an adjustment by even 2050. So what we have is basically a nice little collection of what I think are unusual energy inventions, which our institute often portrays and reprints every month at the by email, and it's an e-news free service called Future Energy e-news. And if you go to our website homepage, integrityresearchinstitute.org, then you can subscribe, and you do need to subscribe personally to this for free, to the Future Energy e-news subscription on the right-hand column. So I was on CNN talking about this stuff years ago as well. And what we see in the energy consumption of various, in this case, 4 sample nations, big ones, India, Germany, United States, and China, is that there are different profiles of energy use. India and China seem to be provocatively, dynamically using coal. That's the black stuff. I don't know why they picked the black color for coal, but obviously there's a reason. And oil and gas have gone up dramatically in the United States. Germany, interestingly enough, has gone down. And what's this green stuff? Oh my goodness. Green energy? Well, wind, solar, geothermal, and biomass. So, and there are more countries, and you'll see the roadmap for how more countries could follow that little green area to make it bigger and bigger. What's interesting too is as you look at the historical annual increase, I think I'm losing the volume anyways, historical annual increase of carbon-free electricity, there is, interestingly, also this comment that nuclear power has exceeded other renewable energy growth. And that's sort of a good complementary technology for the renewables. Because as we master the disposal and the perhaps phototransmutation, nuclear transmutation of nuclear waste, and there are some great technologies now, and there has been even the Paul Brown technology for doing so. Nuclear can be even included in the Green Deal, in the New Deal that has been proposed. So we see how solar and wind is dominated, but also the blue stuff is green, is the nuclear. And in many countries, nuclear has dominated their growth and their carbon-free electricity. So we have to pull out all the stops when you consider the environmental impetus for responding to this kind of emergency. And so to tell you the truth, when I was born, there were less than 3 billion people in the world. Now there's over 6, about 7 actually. Whoops. And I just did it. I touched the side of the remote. And so by 2100, actually 2040, we're going to be looking at 9 billion. So we're going from 6 billion to 9 billion, tripling population in my lifetime. And of course, even carbon dioxide is expected to triple by 2100. So this is kind of a real demand for new energy, and hopefully it won't be more fossil fuel stuff. And this is where some of these articles are encouraging, including the fact that Jim Hansen has contributed some of these provocative, cooperative ventures, talking about quadrupling nuclear powers and getting cooperation between China and the US, which would be great if we could do that on any technology whatsoever. If you haven't already, I highly suggest you visit one of these websites. Empowered.com is one of the best. They have the most reliable solar-powered lanterns, and we have them all over our house. We have them in the backyard, we have them indoors, we have them right above the dryer. Any place you need to see something and you want to turn a light on, why not use solar-powered? And what's great about these lanterns is, you know, if they go out, you just hang them in the backyard, you know, for a few hours or whatever, and all of them have built-in batteries, so then when you bring them back in, they're good anytime, day or night. We also have the type that go on in the backyard by themselves, and even are motion sensitive. So to me, this is the future, and even one of our previous presenters was talking about the dark side of solar power. Well, if you have something like this that's hanging around your house, the idea of losing the grid power isn't so catastrophic. Because you can actually use some of these. And I have a pretty big one in the backyard shed that goes right across the ceiling, and it has a solar panel that's wired to the roof. So it actually charges up, and I just turn that on anytime I go way back in the backyard with no wiring from the grid whatsoever. Some people talk about the possibility of a whole city getting off the grid. Well, they've actually done it, Fort Collins, Colorado. And RMI, I don't know if you've seen this website or received their newsletter, but if you are a member of IRI, then we once in a while do get a whole pile of these. It's called Solutions magazine, and this is Rocky Mountain Institute, rmi.org. And I suggest, you know, visiting that website. They have an amazing annual report. They have billionaires and millionaires supporting them now as well. Amy Levins is a really interesting, very entertaining scientist. And he started just with his wife with this institute, and now it's grown into really a worldwide movement that advises all kinds of military, industrial, commercial clients. So back to the story at hand here, what they're reporting on and they help do is super efficient district geothermal heating and cooling. And this is important because the United States is one of the best sites for geothermal. And I'll show you one of the graphs that talk about that. And so they're talking about the 75% below code and the life cycle and financially attractive. So this could be our future, and hopefully it will be. And along with that are buildings that power themselves, which actually you see here in Kazakhstan. And this was done for Expo 2017. And they're talking about cutting emissions 6,000 tons. We currently are up to 40 billion tons of carbon dioxide worldwide up into the air every year. And it stays there. And we've been doing it for years. We got up to, I think 10 years ago it was 25 billion. And now we're up to 40 billion. So this is great when you talk about thousands of tons, because obviously that's an important number. I think I'll have to grab this other laser pointer here. Okay, now here's one of my heroes, and I cited him when I was in Korea for a conference on energy there, and I've used this a couple times in other places as well. This is from Stanford University. This is basically the possibility, it's the roadmap for the possibility of 139 countries to get to 100% renewable. And you know, no, I don't think any of us believe this is possible. And he's received a lot of criticism, of course. He has some very convincing videos on YouTube, and I do have one which I hope will actually play when I click on it this time. And he's analyzed everything, including jobs lost, jobs created, because when you switch industries, of course you're going to lose jobs. And some of them need technical training to be able to be ready for the newest innovation that obviously all of these solar solar and wind and geothermals and hydros, they all require technical people that are acquainted with this new industry that's going to replace what used to be a fossil fuel industry. So they're talking about the 42% increase in demand by 2050, and this is essentially a comparison between business as usual, staying with fossil fuels, and going into the wind, water, and sun. Okay, so now let's see if we have a pop-up video. See, and all of a sudden this video's there. How about that? Unbelievable.
This figure shows the timeline for transition to 100% clean, renewable wind, water, and solar power for all purposes among 139 countries, and also what would happen if we don't transition to 100% wind, water, and solar. First, the top line, well, it shows from 2012 to 2050, it shows the business as usual projected end-use power demand, which is the top line. So in 2012, there were 12.1 terawatts of total power used for all purposes, as electricity, transportation, heating, cooling, industry, agriculture, forestry, and fishing, worldwide. So end uses means what people actually use to power their cars, to run light bulbs, or to run a dishwasher, or run industry. So end uses, that does not include transmission distribution losses, for example. But those end uses are expected to go up if we don't transition by 2050. Those are expected to go up to 20.6 terawatts per trillion watts. However, if we electrify all energy sectors and provide them electricity with clean, renewable wind, water, and solar, electricity demand is expected to go down about 42.5% to about 11.84 terawatts. Now, 23 percentage points of that reduction, or a 4.7 terawatt reduction, is due to the fact that electricity is more efficient than combustion. For example,
isn't that interesting?
An electric car, 86% of the electricity going into the car goes to move the car, and the rest is waste heat. For a gasoline car, only 17 to 20% of the energy of the gasoline goes to move the car, and the rest is waste heat. So the end-use power demand actually decreases by a factor of 4 to 5 in most transportation types, and that results in on average across all energy sectors about 23% reduction in power demand. Now, another 12.6% of all energy worldwide is used to mine, refine, and transport fossil fuels.
We avoid the fossil fuel extraction.
So by going to wind, water, solar, we eliminate all that energy use because the wind comes right to the turbines, the solar comes right to the panels, so we don't need to mine.
Isn't that amazing? It comes right to the receiver, right to the generator. I thought that was great. That's right. It's free energy.
End use energy efficiency beyond business as usual scenarios, and this includes reducing energy use. So a total of 42.5% reduction of power demand by going to wind, water, solar. So we need to satisfy that 11.84 terawatts in 2050 by 100% wind, water, and solar. So this plot shows that we can do that with around 23.5% onshore wind, 13.6% offshore wind, 31% utility scale solar, 26.5% rooftop solar, both residential and commercial, and then the rest of it, 4% hydroelectric power, 0.67% geothermal, and tiny amounts of tidal wind. Now, this is among all 139 countries that we examined. This is the average power distribution for those 139 countries. Now, the timeline for transition is given here as about 80% by 2030 and 100% by 2050. In other words, we're going to transition about 80% of all conventional fuels, that includes fossil fuels, biofuels, and nuclear power. We're going to propose to transition 80% by 2030 and 100% by 2050. And the result of this will eliminate emissions associated, or energy emissions associated with global warming, and will eliminate all energy emissions associated with air pollution mortality. 4 to 7 million people die each year prematurely from air pollution. So these plans should eliminate most of that problem, and will eliminate most global warming, although the impact of temperature impacts will lag behind the emission changes that will apply. The other results of this study are that the transition will create 24 million net long-term full-time jobs over those laws. So beyond those laws will create 24 million more. Will stabilize energy prices because fuel costs are zero, and will reduce the overall cost of energy to society because we eliminate health and climate costs, and the direct energy costs are similar for wind, water, solar versus fossil fuel. So we reduce the overall cost to society by eliminating the health and climate costs in particular. We also reduce terrorism risk, and we reduce disruption of power supply because we have more distributed energy sources. And distributed energy is more difficult to mechanically break down a bunch of wind turbines or solar panels compared to centralized fossil fuel or nuclear plants. And so that reduces risk to power disruption. And because in the annual average, these plans call for all countries to be energy independent, essentially. Each country should be able to provide their own power in the annual average. This could reduce international conflict. However, it won't be advantageous to actually transmit energy between countries to reduce the prices of cost of energy even more. So in sum, we find that it is technically and economically feasible to transition to 100% clean renewable wind, water, and solar in all energy sectors among 139 countries of the world that we examined. These countries represent more than 99% of all emissions, and we think the rest of the countries should also follow suit as well. Thank you for paying attention to reading through.
So this was published in, Nature, Jewel magazine, and also another prestigious journal. I think it was Nature. He's at the Carnegie Institute here in DC as well, or they're in DC where I usually am. And this is a summary, what you're looking at, 2050 jobs and so forth. And I think we covered all these numbers in the video you just saw. So this is one scenario using conventional energy that actually could make the difference in the future. And of course, this is something that requires each country to make up their mind that they want to get on board. And there's lots of countries that are now motivated. There's, for example, 17 countries I just heard this past week have a water shortage. India, for example, has one city where they're literally trucking in by train bottles of water because the entire city has no water. So this is becoming an issue environmentally as well. Now, one other technology, which I'm hoping this will also, and I was asked about this technology earlier today, is the idea of capturing waste heat. Most people think waste heat is almost useless. And this particular video is another one that very short, but also very technically. Okay, this was over 10 years ago. MIT did an analysis, a study on geothermal throughout the United States. Geothermal keeps growing very slowly. We actually had a presentation at our conference, COFE, about 5 years ago, by a local person in the Washington, D.C. area, who literally, before he built his home, had them drill, I think it was 100 feet below the property. Jim Ott was his name. And he tapped into the geothermal heat right below his house, then had the house built around it, and now that's all the heat he needs. And he's, it's basically 2 pipes that go down with a little connector at the bottom. And that's how simple it is to tap geothermal throughout the United States. And it's probably a matter, if you ever wanted to do it on a property of your own, getting a geothermal expert to at least analyze how far down it needs to be drilled and what it would cost. But it's a one-time investment. So right here we're looking at 2,800 megawatts, which is basically about 3 gigawatts. And the estimate now is up to around 6 gigawatts or more that are available from geothermal plants, and lots more than 4 million could be supplied with electricity from geothermal. And this is just water vapor that's coming out. So this is really a very clean technology, and obviously MIT advocated that it should be more widespread here in the United States. One thing that I was surprised to find is the idea of bacteria being such a vibrant agent for converting waste into clean energy and clean electricity. And what we find is there's a particular type of bacteria, Geobacter strains, which is a GMO bacteria, but hey, it's worth it when you can modify them to really work for you. And they grow slowly, do not create microbe cakes, and this is a company, Cambrian Innovation, that worked with the Naval Surface Warfare Office in Maryland and scaling up to from 2,000 liters a day to 20,000 liters a day. And what you're looking at is a self-powered wastewater treatment plant using microbes that essentially is self-powered. And this is also present in the Washington, D.C. area. And here's a local farm, which I saw on, I think it was on National Public TV, where the local farm was using something similar, and it was developed and facilitated by the University of Maryland, as well as Penn State University. So there's various types of ways to make use of that. And the technology breakdown, as far as a flow chart is involved, is using the bacteria as the electrolyte. And therefore, the organic chemicals are supplying CO2 on one side and the oxygen and water on the other side. And Craig Venter Institute, which is pretty famous, is testing 600 liters a day from pig waste and the local farm in Escondido, California. And as I pointed out, Penn State is looking at kilowatts that they're already generating in test facilities. And this is Penn State's little tabletop prototype showing how they got approximately 1 kilowatt hour per kilogram of waste. And the information is that it could be, I think, used here in Brooklyn's Newton Creek wastewater treatment plant, where currently they're consuming almost 1 million kilowatt hours of electricity, and instead they can actually generate 350,000 kilowatt hours a day. So there's enough energy for 11,000 people. So what a transition to go from consuming to generating. And this is a very, I think, I'm proud of this discovery to find out the city that I live right outside of actually has one of these, and it's generating 13 megawatts of electricity from little old microbes, busy at work. So every flush is harnessing electricity. Thermal hydrolysis. And this is Norway's technology. Norway really pioneered this stuff. And there's other places like dairy farms and so forth that are getting on board as well. So this is the future, folks. It's really, you know, one's here, one's there, but they're all seminal samples of how this can become mainstream almost everywhere. And of course it needs to be, because who wants to be plugged into various types of environmentally unusual sources that consume energy. So in terms of energy harvesting, it's really a $7 billion market. Energy harvesting, triboelectric energy, even the idea of creating burnable fuel from carbon dioxide and water, that keeps recurring in the news that we find and we keep throwing into our future energy e-news. Even self-powered systems are becoming the mainstay for many headlines from various energy harvesting sources. So this is a new buzzword. Energy harvesting incorporates and encompasses many of the topics we've seen yesterday and today at our conference. And I think future energy, if they start using a buzzword like energy harvesting, can benefit from that, because then you welcome a lot more engineers who are acquainted with this phrase, but unacquainted with your particular niche technology. And of course, even if it's speculative, this is a hot topic. For example, what if you could generate electricity from the clothes you wear? Well, that's something that we're actually exploring because we have a patent on antioxidant electric clothing. And the only drawback or the hurdle we have to overcome is what type of power source should we use? Well, I like this one a lot. I've tried to contact the Nanotech Institute that has discovered this. And these are coiled carbon nanotube yarns, University of Texas at Dallas, that generates electricity when stretched or twisted. You don't do any stretching or twisting during the day, do you?
Well, your body is constantly moving, so your clothes are constantly moving, so there's a potential for energy harvesting there.
Thank you, sir. 250 watts per kilogram. There you go. So those are significant numbers. And as we move on to other topics of breakthrough energy, the electrification of the personal vehicle is actually becoming more and more mainstream. 87% could be actually electric cars because of the miles you drive per day. We're considering that possibility of transitioning to electric vehicles as well. And the only thing that's holding people back, they found in studies, 90% of all travel is first of all, the range you travel and the average is within the range of the electric vehicle's capability. But often people have range anxiety involved in that. But overall, there's a lot of different technologies now, for example, in small communities and even one overseas country, that's now incorporating electric cars into the grid. So the local grid of renewables can benefit by using the electric car's battery as a storage medium. And they collect them through the computerized version of all the electric cars that are available. And they're just mandating electric vehicles for the entire small country. But 35% of sales now by 2040, that's one of the estimates from Bloomberg Finance. And the graphs here, you're looking at 2016, a lot of summer purchases that are peaking. And each one seems to exceed the previous year's total. So overall, we're seeing an increase in electric vehicle purchases. Some of the breakthroughs that we do follow as well that complement electric vehicles are not only my spiral magnetic motor invention that I'm working on, which is moving along pretty well thanks to the Hathaway Consulting and Research Institute. But things like the 24M lithium-ion battery, that's a flexible one that cannot possibly burn or explode, is certainly interesting. And the price tag of less than $100 per kilowatt hour is very attractive. So we're following this one. This is only a couple years old, MIT Technology Review. And they were projecting scaling up for high volume right in this time period. And it has more capacity than current lithium-ion batteries. One thing I do like, and I've seen this is a Japanese invention, is the idea of putting solar panels entirely on every single top surface of a vehicle. And that's what they're talking about here. A solar-powered car driving 50 miles on a 5 to 6 hour charge. And if you run out of electricity out in the desert, you just pull over and park for a few hours. That's all. So you don't have to even look for a charging station, which is kind of the transition to the onboard charger that we are envisioning. And this is a new breakthrough that actually is quite exciting. The concept, which we got to give Jim Dunn a couple kudos for this, because he was the first to consider and build an electric-powered plane. And now it's actually being envisioned by NASA as the mainstay for a commercial jet. And the interesting storage medium is using liquid hydrogen, but essentially converting that through a series of fuel cells. So it is electrically powered, but hydrogen is still being the source of the energy. And NASA is funding the project, University of Illinois. Now, when you talk about water, under seas and far in the offshore are probably the two best places to place windmills. And of course, an undersea turbine is even better because you never get to see it at all, except maybe the buoy that's sticking on top of the surface of the water. But 200 megawatts is not something to sneeze at. And the Department of Energy has been giving grants to this. Even Mitsubishi Heavy Industries have been to it. And they've already been building this Isle of Wight and the Wales country looking at the Gulf Stream to have major installations for this as well. And these are long-term installations that generate quite a lot of energy. So what's, in terms of breakthrough, I would say this certainly is one of the biggest breakthroughs which was under the radar and never made the front page of the news. What's interesting is the universities, Harvard and Columbia, were responsible for discovering this. I found it on a small little video that I used to show. It shows a polymer flipping back and forth when it's wet on a wet surface. And it was hard to imagine that humidity or water itself could be a source of power just by evaporation. But what these university kids, probably grad students with nothing better to do, put together this motor, and with bacteria to help in the bending of this little polymer, spores are on one side and the wet surface on the other, they tend to bend in one direction when they're wet and another direction when they're dry. So it creates an unbalanced force, and there is a video online which I used to show, and this may or may not actually function. Let me try it. I'm willing to try one more time here for videos. Okay, so we're going to the internet to see if this actually runs. And it ran last night when I tested it one more time. But okay, and I guess we'll click on the play button here. It's a supplementary movie. See, that's the thing, it's supplementary. And there's moisture at work, folks. Columbia University is getting the credit for it with their little sign. And of course, our internet is now a little intermittent. And this could be Mike Gamble's little four-wheeler, who knows? But it's amazing to see that water itself and evaporation is actually a source of energy. And obviously, energy and propulsion go together. That's what our institute believes and also has promoted quite a lot. Anytime you have an energy invention like this, here's a way to develop propulsion from it as well. So, and we can like it or dislike it, obviously, as well. So we proved that it really works. And the conclusion of that particular segment is, ta-da! Energy harvested from evaporation could power much of the United States. And much is like a big majority, in other words. So Columbia University is promoting this big time. And this is essentially devoted to lakes and various mountain lakes that are essentially unused, so that if you cover the surface of the lake with this type of converter, then you're not interrupting too much tourist use of the lake and so forth. So, but they did do a study to find how many abandoned lakes, so to speak, even reservoirs, so forth. There's lots of examples of that. And we do have to give some credit to Walt Jenkins and Maury King for bringing to the fore the amazing invention that as you add water with a piezoelectric component to vaporize a fuel mixture, the water actually aids in the combustion process. And this is a patent application in 2012. So we hope to see this actually granted by the Patent Office. I'm not sure. Has it been granted yet, Maury? It has?
Canada granted, you're still waiting on the U.S.
Of course. We're still waiting on the U.S. Patent Office, as usual.
That's where you're going to help.
Waiting for Godot. So clean fuel for a clean future. Yay! Yeah, I hope Walt gets enough funding to make this mainstream really soon. This would be a solution to fossil fuel usage right away. And speaking of water, this is another twist that I thought was unbelievable, but worth mentioning, because when you think of an entire power plant devoted to the difference between seawater and river water, which is fresh water, there's now a couple more inventions using the same kind of concept, where there's a salinity gradient that actually can generate electricity. This uses a special membrane to do it, in terms of kilowatts of electricity, and it's called the Osmosis Process. We have a report on that, but now I'm seeing that there are other even more direct routes for using the same thing. And this example of a river falling into the sea and combining close to the saltwater body is actually present a lot of places throughout the world. So the extractable water is available. And finishing up with this standard technology business, the idea of using highways themselves as generation stations is also a very hopeful transition that we're now seeing happen in California. This was a company, Innovatec, that was in Israel for years promoting this product, and it was essentially a piezoelectric panel under roadways and also under railways that reacted to the weight of the vehicle passing over it. So there was a very reliable solid-state means for generating, and stand back while I repeat the numbers on top, 0.5 megawatt per kilometer. So when you talk about megawatts, that's big deal. You know, this is not milliwatts or microwatts. So that's why the California highways now are involved, and there's a corporation that's actually spearheading this test in California. So hopefully we'll start to see this on American highways as well, and perhaps around the world. In terms of wireless power, there is a new company, which I forgot to throw in here. It's no longer TexonT.com, but there's another company that took over this technology. I don't think Jim Corum is associated with them anymore, but he did contribute to my book on the topic. And perhaps the biggest breakthrough that Jim Corum made on this, and he contributed to the book, is the fact that the Xenic wave is the unusual complementary transition or transmission channel for wireless electricity. Not only is the Earth ionosphere cavity, but also the Earth itself. So the combination is very efficient. And I thought I'd throw in just a little bit of propulsion real quick, because it's kind of fun to talk about. Ancient Aliens was one chance I got to do that. And you're all familiar with what Mike did. But this was back several years ago in 2012, when I was lucky enough to catch this first photograph of this amazing room-size control moment gyro that I never thought we'd possibly get to be presented here at COFE, and even transition into a tabletop model. But we're hopeful that even the KID patent and many others can actually see the realization of that. And in terms of propulsion, the idea of inertial shielding has been mentioned a few times in various presentations here, but to explain the inertial concept, I think is very important for people to understand, because first of all, Hayes predicted this in Physical Review A in 1994. That inertia is a 0-point Lorentz force. And this is important in terms of the standard F equals ma, Newton's law, because inertial mass is what m is really describing. And as we bring m down to close to 0, then you're actually looking at an extraordinarily high A for the same amount of force that you provide. And I've had a lot of discussions with people that are aware of this technology or claim to have that, and they say, well, yeah, your vehicle is so light that you just touch it with any small, even electrogravitics, would be sufficiently powerful to move something that has virtually no mass. And therefore, that faster than light and even turning on a dime, all of those things are possible when the inertial mass is very small. Because those are the two things, accelerating quickly or turning, that are responsible directly from inertia. And the idea of a shield, whether it's electrostatic or some other type of I've heard of aluminum with the iridium involved in it. Whatever it does, what Hayes predicted was you're no longer interacting with the electromagnetic quantum vacuum around you. So therefore, you're isolating yourself from what is really a Lorentz force caused by the electromagnetic physical vacuum that consists with electron-positron pairs. And this is his article. I forgot that I had the slide. I'm pointing at the diagram, but this is the actual one. Hayes-Shorett input off, 1994, inertia as a zero-point field Lorentz force. So, and this is his famous line that I thought was very important. Resistance to resistance to acceleration results from this Davies-Unruh effect, which is really a Lorentz force when you look at the equation, F equals V cross B, which all of us know when you take even high school physics. So overall, we can view this as the complement to the gravity being a zero-point Lorentz force. And in general, the recognition of that was even seen in the various science fiction books as well. And overall, it could be the basis for a space drive. And so electrogravitics is now, I think, having a lot more validity, even if it is providing a very weak force, either from ion wind or as the Jeffimenko equation provides, the concept that it actually can be presented from the electrokinetic equation. And this was actually a serendipitous discovery of mine when I wanted to write the introduction to the book, Electrovitics 2. And by the way, I do include this very interesting paper by Mark McCandlish. And it took me about a year to get permission to include it. And this is his drawing of what was demonstrated in Norton Air Force Base in 1988. And this big, heavy metal object was hovering. And it works on the same principle that is in the Electrovitics 2 and Jeffimenko prescribes, which even Zinsser was using and others, and that is pulsed electrokinetics. And even when Paul talked about very high nanosecond rise time on your high voltage, this is the equation that actually shows the d I dt. In other words, if you can make this transition very high and very large, a lot of current for a very short time, then your force that you're creating is going to be very large as well. And that's exactly what Jeffimenko predicted. I even wrote to him and asked him if he knew about Townsend Brown's electrokinetics, and he didn't. So this is like parallel genius development in two camps of the same concept of electrokinetics. But the pulsed electrokinetics I really have to give credit for. And by the way, when Paul Murad mentioned Jeffimenko's co-gravitation, well, that's the other half of this book, causality, electromagnetic induction, and gravitation. Jeffimenko put 3 different topics in one book. So this is the first topic, talking about electrokinetics, and then the last half of the book is on his co-gravitation theory. So Jeffimenko is certainly a genius in himself in many ways. And to finish up, I thought I'd throw in a little UFO picture of one of my favorites. And I started in this whole field of free energy and unusual breakthrough technologies dealing with energy and propulsion back in 1980. And this was following up on what was the book that I read called Sunburst: Return of the Ancients by Norman Paulson. You can still get old copies on Amazon, for example, and it's good to get the old hardcover, because what Norman did is started to censor his own book. He didn't even want to include the paragraphs that he claimed were an actual quote from the aliens saying this generator will be self-perpetuating if you had magnets around the outer edge of a rotating disk. And so I was encouraged in 1980 to pursue this as a master's project in physics, which I did. There's my little insert picture of the actual homopolar I built, and I got a master's in physics just because I built that thing. Plus I had to take some courses, of course. But it was fun to propose the project to my professor rather than wait for the professor to propose a dumb project to the student, you know. So, okay, so my highlight of this slide is, of course, this amazing parallel page on the book that I'm citing, and that is the deputy sheriff who took the picture you see on the left with what looks like a saucer-shaped object hovering in broad daylight above giant rock outside Los Angeles, California. And people are walking casually around, or you can even see some of the force lines below it. And there he is holding the photograph, and it adds, I think, tremendous credibility to the photo that you're looking at. So the whole story was that this was not only a good propulsion system, but also an energy source. And so I was encouraged to follow through with even 2 different disks, supposedly rotating in opposite directions. We'll see where that takes us. But I also considered the fact that the Searle device was a very similar description. So most of the topics that we discussed are found in the various books we have available through Amazon and elsewhere. And follow our IRI conversation at futureenergy.org. Thank you very much.
Forward to 2050. The world's population has grown to 9 billion. That's 2 billion more people added to the planet over the last 40 years. In addition, millions of people are enjoying a better standard of living, so energy demand has shot up, doubling our current rate. At the same time, scientists believe that CO2 emissions will need to be halved to avoid serious climate change. What's shaping that future? Millions of people across the developing world are improving their quality of life. They're buying their first fridge, computer, or car. If we all continue to use energy the way we do today, energy demand by 2050 could rise by even more, perhaps as much as 3 times the current rate. Shell scenario planners think a big gap between energy supply and demand could emerge. That gap will have to be closed, either by demand being forced down, or supply being ramped up, or some mix of both. But just how that will happen is uncertain. So, the world will face a zone of uncertainty. We will have to draw on many different sources of energy to meet our needs. By 2050, a third of the global energy mix could come from renewables. Fossil fuels and nuclear power are likely to make up the rest. The future will also call for greater energy efficiency and more lower CO2 options. How is Shell responding? The challenge is a big one, which the world will have to tackle together. At Shell, we're working with partners to deliver more energy, investing heavily over the next few years to develop new sources of oil and gas. We are producing more natural gas, which represents cleaner energy, as it emits up to 70% less carbon dioxide than coal in power plants. We are developing smarter energy through products and services that help our customers get the most out of the energy they use, boosting efficiency and cutting their CO2 emissions. Innovation from Shell, helping meet the world's growing energy needs in a responsible way.
We think that it's possible to address all of global carbon and air pollution problems simultaneously by transitioning every single country and state to 100% clean renewable energy, particularly wind, water, and solar power. We calculate 22 million new jobs worldwide by such a transition. Onshore and offshore wind, solar photovoltaics on rooftops and in power plants, utility-scale solar photovoltaics, also utility-scale concentrated solar power, and then geothermal power, existing, not new, hydroelectric power, and tiny amounts of tidal and wave power. And we find for each country of the world that we tested that it's possible to power each country entirely by wind, water, and solar. Electricity is much more efficient than burning things. For example, take a gasoline car. A gasoline car, only 17 to 20% of the energy in the gasoline goes to move the car, and the rest is waste heat. If you have an electric car, of the electricity that goes into the car and is stored in batteries, 80 to 86% goes to move the car. So we reduce significantly, over 60-70%, the energy need in transportation. When you average over all sectors, there's about a 32% reduction in energy demand due to this efficiency. And then we can squeeze out another about 7% end-use energy efficiency improvements beyond that. So we get about 39% reduction of power demand over all sectors. So the problem with wind and solar, for example, is the wind doesn't always blow, the sun doesn't always shine. So the concern has been that the grid will be unstable, you'll have high costs to keep it stable if we go to large-scale wind, water, and solar power. But it turns out this is not the case. It's actually the opposite.
In 2014, more than a fourth of Germany's electricity consumption was renewable, and about half in 4 other European countries with modest or no hydropower. None of them added bulk storage. All of them sustained high reliability, for Denmark and Germany about 10 times better than America's.
The actual demand is variable itself. Okay, so baseload power doesn't really mean anything, because you always, even today and historically, you've always needed some kind of peaking to fill in the gap. So like nuclear power, which provides baseload, does not help you actually match power demand. Coal, which is primarily baseload, does not help you meet the peaks. It just gives you kind of some flat underlying amount of energy. But we found that by electrifying all sectors, so that's transportation, heating and cooling, industry, in addition to electricity, it actually makes it easier to match power demand at a cost of about 10.5 to 10.6 cents per kilowatt hour, which is similar to the energy cost of a fossil fuel system.
Waste heat is finally valuable. Introducing the E1 Thermoelectric Generator. Saving fuel has the potential to be one of the biggest levers a company has in reducing its operating expenses. With the E1, that potential is finally realized in the world's first waste heat recovery product to meet the oil and gas and mining industry's criteria for a strong, simple, reliable solution. When we set out to build the world's first industrial-scale thermoelectric generator, we knew it had to behave as a piece of simple industrial equipment rather than a complex power plant. What resulted was the E1. The E1 takes waste heat from exhaust and simply turns it into electricity. The result is an engine that delivers the same amount of power, but with less fuel. Recognizing that downtime at the customer's site is a non-starter, we designed the E1 such that installation can occur in just 2 hours with almost no upfront scope. Every part needed comes inside the E1's simple and easily transportable 16 or 20-foot shipping container. There are only 2 points of connection. First, the E1 flanges directly onto the exhaust pipe. Then, wiring is run from the E1 to the site's main breaker. The E1's operation is simple and reliable. Exhaust from the engine is channeled through 32 modules that generate power in the solid state with no moving parts, using Alphabet's proprietary PowerBlocks thermoelectric technology. The DC electricity is delivered to the prepackaged power electronics, which invert the power to AC at the same phase and voltage that the engine delivers. The cooled exhaust then flows up and out of the container at about 200 degrees Celsius, while the E1's prepackaged radiators keep the modules cool. The modules inside the E1 are revolutionary because they include the only efficient low-cost thermoelectrics ever made. Like everything in the E1, they've been rigorously tested in the field to ensure at least a 10-year life. And they're fully upgradable, making the E1 the only upgradable power generator in existence. As Alphabet continues to make advances in thermoelectric materials, new modules can be swapped in for old ones in the same system to generate even more fuel savings. We talked to hundreds of customers who spend their days looking for ways to improve operational efficiency and profitability in their businesses and have the most demanding requirements for equipment in the field. With the E1, waste heat is now valuable. Some of the smartest, most forward-thinking companies in the world are using the E1, and we're excited to help a range of industries reduce their fuel costs and drive profitability by using waste heat.